Hello and welcome to the 7th episode of the Innova Biosciences webinar series. Today's webinar, Gold Nanoparticles, Strange Properties and Applications in the Life Sciences, will discuss the extraordinary properties that gold nanoparticles exhibit, which are quite unlike those of the bulk material. These properties can be exploited in a variety of assay applications, including lateral flow tests, microscopy, flow cytometry, and FRET assays. There are also a number of therapeutic applications, especially in the field of cancer. This exciting webinar will focus on the following points: an introduction to gold, the unique properties of nanoparticles, why does 40 nanometer gold never look the same from different suppliers, methods of attaching proteins and analytes to gold, uses of nanoparticles in diagnostics, and uses of nanoparticles in therapeutics. Our speaker today is Dr. Nick G. Nick is a biochemist with over 20 years experience in the pharmaceutical and biotechnology industry and is the CEO and CSO of Innova Biosciences. Nick did his PhD in Leeds on the development of hybridomas and use of monoclonal antibodies to localize and purify membrane peptidases. He subsequently took up various research positions in the pharmaceutical and biotechnology sector with Merck, Warner Lambert, and Upstate Biotechnology, and has expertise in protein purification, assay development, and bioconjugation systems. Nick is the inventor of the Lightning Link antibody conjugation system and the Innova Coat gold conjugation technology.
Hello, everybody. If we mention the word gold, these are some of the objects you perhaps think about. Certainly, most scientists would think of, a yellowish material. Most people wouldn't think of gold as being red. In fact, it can be many other colors too. So this first slide really describes why gold nanoparticles can have a red color. So this really applies to nanoparticles in the 10 to 200 nanometer range. There's an electron cloud around the gold particle, which can be excited by white light. So the energy that is absorbed essentially means that gold displays a red color. Now when the light hits the electron cloud, the cloud begins to oscillate, so there's some polarization. So as the negative charge dips down, there's a positive charge on the metal core. So this acts as a restoring force, so the electrons bounce back. So you get this resonance situation, which is called plasmon resonance. And as we'll see in the following slides, gold nanoparticles display shape and size dependent properties. So often they're red, but you can get an amazing range of other colors too. You also get proximity effects. So if the gold particles approach one another, for example by aggregation, or more usefully in a controlled manner by design, you can get a color change. Usually the color is red shifted, so you either get a blue or purple color. In this slide, you see on the right-hand side a tube of gold nanoparticles with the red color. These are 40 nanometer particles. And on the right, the particles have been aggregated. So if you do an absorbance scan, this can confirm really what your eye tells you. So this is the what is called the plasmon band for 40 nanometer particles. Absorption around 520, 530 nanometers. And then in the aggregated state, there's a dramatic change in the profile, particularly in this region where there's a significant increase in absorbance between 600 and 700 nanometers. So if you take a ratio of, say, 650 to 530 nanometers, this is a useful aggregation parameter. Although you could take more or less any wavelength in this region and express it as a ratio of 550 to get a measure of aggregation. Okay, turning to gold rods. So again, these clearly have a defined shape, and it does affect the color. So in this particular case, when the light hits the outer electron layer, you get both longitudinal and transverse plasmon resonance. So you get an additional absorption peak very much red shifted, so rods appear as blue or brown depending on the aspect ratio of the gold rod. So I think the slides you've just seen provide a few clues as to why 40 nanometer gold looks different from different suppliers. And here are just 5 examples, so 5 tubes just against the white light background, and you can see they don't look the same. This is a bit disconcerting when you first start working with gold, because you know, what if your current supplier runs out of material? It's not such a straightforward matter just getting identical material from someone else. So why do these appearances look different? Well, again, we can just look by absorbance scanning to confirm what our eye tells us, and when you see 5 profiles like this, they on the face of it look quite similar, but when you overlay the profiles you can see that there are differences. So why are there differences? Well, if you go to look at the particles by TEM, transmission electron microscopy, you can see that they really are quite different. So all of these particles are 40 nanometer gold, or described as such. This is the scale at the bottom here, 50 nanometers. So for example, in the top left you can see that some of the particles are maybe a little bit small. You have some rod shapes. This one, you have this spectacular triangle. Again, some spherical particles. In this particular case, middle bottom, there's a huge particle there, but some smaller ones. And here we have spherical particles of about the right size with a rod. This one is strikingly different from the others, where the particles seem to have fused together in the production process. And here we have some spherical particles of about 40 nanometer size. So the reason they look different is because they are different. And if we go back to the absorbance scan, what you have in this region here is a shape-sensitive region. So the absorbance scan provides a lot of information about your nanoparticle suspension. You also have a size-sensitive region here. I'll come back to this. In this particular case, as you'd expect, because they're all 40 nanometer particles, then they do have a plasma band which seems to be consistent with that, despite the fact we know from TEM that the 5 suspensions are different. Okay, just a cautionary note about absorbance scans. 40 nanometer gold gives this profile with a fairly narrow plasma band. These are spherical particles. Now, if you have this profile, it doesn't mean you've got 40 nanometer gold. You might have, but it doesn't prove it. And I'm going to illustrate this with 20 nanometer and 80 nanometer gold, which give these profiles. So this is 20 nanometer, 80. When you overlay the curves, you can see that the 80 nanometer size is right shifted. So this is the size sensitive region, and the 20 nanometer plasma band is shifted slightly to the left. Now, if you mix these two things together, the question is, well, what would happen? What would you see on an absorbance profile? So you perhaps think that you would see a broad peak, perhaps with a double peak. Seems logical. But what happens when you mix together 20 and 80 nanometer gold? You get a single peak. You don't see the two components. And when we superimpose all 3 curves now, you can see that the mixture gives a single peak right in the middle of the 2 components. So this is a peak which is consistent with 50 nanometer gold. In actual fact, you have 20 and 80. So this just highlights one of the unusual properties of gold. It doesn't behave like a mixture of colored organic molecules where you would just the absorption curves would just be additive. This gives you a single average profile. So You have to be very careful with the interpretation of absorption profiles, but they can give very useful information. You just need to be careful. Okay, so just to summarize the first section of the presentation, 40 nanometer gold looks different from different suppliers, really because it is different. The particles have different shapes. The plasma and resonance band, and thus the color, is markedly influenced by shape and by interactions of particles with other particles, which also really is changing the shape. And absorbance scans provide useful quantitative information, but careful interpretation is required, especially about the size of the nanoparticles. Okay, just moving on to the next section, covalent attachment of molecules to gold. Now, I'm sure you appreciate Innova focuses very much on covalent conjugation, but I will be mentioning passive conjugation to gold as well later in the presentation. Okay, if we think about attachment of molecules to gold, you really start with the field of molecular self-assembly, and there's a lot of research done in this area. Essentially what you can do is take thiolated molecules, in this case alkane thiols, which have hydrophobic tails, and thiols have a reasonably high affinity for gold surfaces, so the thiol groups align on the surface and the tails align to give a hydrophobic organic surface. So instead of a metal surface you switch to an organic surface by this process of self-assembly. So the tail determines the surface properties, and if you have a polar tail you'll have a polar surface, and so on. Now, this sort of approach can be used to coat nanoparticles to introduce functional groups, say carboxyl or amine, which are very useful for bioconjugation purposes. So gold nanoparticles tend to come coated with citrate ions, which stabilize the colloid, and if we use this type of molecule, this would represent a successful coating with essentially the gold metal shielded by these head groups. What tends to happen though is you get dissociation. So each one of these molecules, it just has a single point of attachment. It tends to dissociate, and when you get bare metal surfaces you tend to get aggregation. Usually what happens with this approach is you never get to this point. It's very easy to destabilize the whole system when you add this type of molecule. You can go straight to an aggregate, and your eye tells you immediately whether you've got such an aggregate. Anyway, what we've done is to develop what we call Innova coat technology, where we essentially wrap a protective coat around the entire particle, which gives incredible colloidal stability, and we also have a number of surface chemistries which allow different types of molecules to be attached to the gold in an irreversible covalent attachment. Okay, if we put this surface coat around the gold particle, we'd expect it to influence in some way that electron cloud, and there is a very subtle difference in the absorption profiles. You can see that the Innova coat gold is right shifted. It's about 4 nanometers. So it's a very subtle change. It's useful for us because we know for sure when the coat has attached successfully. If we now look at the colloidal stability of naked gold and Innova coat gold, then there's no subtle difference here. There's a drastic change in colloidal stability. So this is naked gold in water, and then we've added either 1 mole of sodium chloride, hydrochloric acid, or sodium hydroxide, and this is an instantaneous change, immediate aggregation, which you can see quite clearly from the profile. If we go to Innova coat gold with the protective coat, you see that the 4 curves are superimposable, so the colloid now is completely resistant to these insults. This is another way of illustrating that the gold particle is completely shielded from the external environment. So we have here 40 nanometer gold, and we've got one lateral flow strip which has been spotted with IgG. So obviously ordinarily you can't see the spot. And what we've done in panel A is run the coated gold up the strip, and then we've washed the strip. And you can see there's no evidence of the spot, so the coated gold has gone straight past the IgG spot. If we now run naked gold up the lateral flow strip, you can see that it flags the position of the IgG spot. So the spot was there when we ran the coated gold up the strip, it's just that the coated gold went straight past the spot. And this is just the wash strip after the naked gold treatment. So this shows that as far as antibodies are concerned, they can't see in any way the metal surface. So any interactions between antibodies and the coated gold is with the surface, not with the metal. Okay, so this takes us to this position. We have naked gold, which is widely available for passive binding of antibody. Binding of antibodies in this way involves systematic pH and salt titrations to try and optimize the binding. You also need a blocking step at the end. As I said, it's widely used, but there's a significant risk of unwanted aggregation. If there's something not quite right about the conditions, you could get a purple aggregate very easily. And this is the coated gold on the right, which is designed for covalent binding. The only thing to consider here really is adding the correct amount of antibody, and it's normally added to freeze-dried gold. Because of the stability, we can provide this material in this freeze-dried format. Often less antibody is required than with passive binding. The gold is already blocked because of the surface coat, and you end up with a very stable product. So we can provide this material in kit form with freeze-dried gold nanoparticles with all the chemicals that you need to carry out a successful conjugation. The only task really is to add the antibody, and the rest takes care of itself. So the hands-on time for this procedure is 1 minute, and the conjugate, which is 20 OD, is ready to use in 15 minutes. And you can do this on a really small scale or a large scale, so you can do optimizations, for example, at 1 microgram scale. Okay, so what we've done with this InnovaCoat surface is to attach other useful functional groups. So we have a maleiamide surface, which can be used, for example, for attaching thiolated oligonucleotides to give this product. And of course, because the oligo is attached to a surface which is irreversibly bound to the gold, this too is now irreversibly bound. It's not going to dissociate. We also have a hydrazide surface. Now this can be used for oriented coupling of whole antibodies. So on an antibody, in the Fc domain, you have sugar chains, and these can be activated. Once activated, they react very quickly to form a stable bond with hydrozides. So the antigen binding sites, which are here, point outwards, and you can get unhindered binding to the antigen because of the oriented coupling. We can also do oriented coupling with antibody fragments. Going back to the maleiamide derivative now, FAB prime fragments, as you would have after digesting antibodies, would have thiol groups in the hinge region, which can react with the maleiamide to orient the fragment with the antigen binding arm facing outwards. This can also be used for engineered antibody fragments, which are very often expressed with a cysteine terminus for coupling purposes. So one of the key points, though, is that there's no protein-metal contact. So small fragments will quite often unravel on a metal surface. There's no metal-protein contact with this particular coated material. Or orient your antibody? Well, you can get improved performance. So this is some lateral flow data with an overcoat gold coupled to FAB, either oriented through cysteine or in a random orientation through lysines, which are distributed across the whole fragment. So you can see that the signal is actually greater with the oriented coupling than with the random coupling. Okay, just to summarize this section, methods of attaching molecules to gold may be passive or covalent. Both have their place. Covalent linking is more stable, especially for small thiolated molecules. And covalent strategies allow oriented coupling to be carried out. This is not possible with passive coating where the orientation is random. Okay, in the final part of the presentation, I'll talk about some applications of gold nanoparticles. Okay, here are just some. I mean, there's a very long list, but lateral flow, which we just touched on, optical sensing, light scattering applications, drug delivery, and cancer therapy. This is another example of lateral flow. This is not our data. This is from one of our clients. So this is a competitive assay for IgA. And the data has been expressed on the left in terms of signal intensity versus concentration, and on the right percent binding. So it's the same data, just transformed in two ways. So you can see with the passive gold conjugation, the signal is far less than with the coated gold, and also the percent displacement is far greater with the coated gold. So you have a far better assay, perhaps because the antibody appreciates being attached to the surface coat rather than to the metal. Okay, another application to do with light scattering. Now, when any particle receives incident light, the light can be scattered. I mean, it could be reflected, which is a form of scattering. And depending on the mechanism involved in the scattering, you might see terms in the literature, Rayleigh scattering or Mie scattering. But whatever the mechanism, the light essentially changes direction, and it can be used to develop various assays where you can sense the presence of gold. And this particular case, the scattering application, scattering is more pronounced with large gold particles than with small ones. So the smaller ones tend to absorb rather than scatter light. So a couple of applications. Dark field microscopy. This is where in the eyepiece you see just scattered light. You can't see light that hasn't been scattered. So you see the specimen against a dark background. And flow cytometry is another well-known application that can involve scattering. So gold is used in these applications, especially the large particle sizes. Another application we've come across quite a lot is SERS, or surface enhanced Raman scattering. You see this more with silver particles than gold, but there is quite a body of literature on gold too. So Raman scattering is connected with molecular vibrations. It's in the infrared region of the spectrum, and if you place a molecule on the surface of gold which is excited because there's incident light to give this polarization which establishes an electric field, then you see enhanced Raman scattering. Normally this is quite weak, but it can be amplified by orders of magnitude if the molecule is at a gold surface. So what you tend to find is that the intensity of the electric field and the enhancement is better with irregular surfaces. So this is perhaps an application where you want a rough surface rather than a perfectly spherical gold object. Another application, optical sensing. This is where we have a binding entity A and binding entity B. The two can interact with one another. This could be A and B, could be an antibody and an analyte. It could be two binding proteins or possibly complementary oligonucleotides. So they interact with one another. The electron fields overlap, particles are in close proximity, and effectively we have a new shape. It's more like a rod than two separate particles, so the color changes. There's some real data now with what we've got here is biotin attached to Innovacoat gold and streptavidin also attached to Innovacoat gold. So the two profiles are shown here, streptavidin gold in red, biotin gold in blue. And when you mix the two together, you see a dramatic change in the profile. There's a substantial increase in signal around 620 nanometers, but across all of this region. So the color changes from red to blue. Now with this type of application, regular spheres are best because they have the lowest signal in this region. Remember, this is our shape-dependent area. If there's any aggregation or unwanted aggregation or any irregularities, you will get higher signal in this region. So regular spheres are great because you see a huge shift when the particles interact. This is the same type of thing. We're now scanning at 620 nanometers. It's a time course. We've got streptavidin and biotin in Innovacoat gold, and you see a rapid signal increase at 620 as the material turns from red to purple. And this is a control where we've got excess biotin, so it prevents the interaction. You can see that the material stays the original color. So that's the principle of biosensing and exploits unique features of gold nanoparticles. Probably worth mentioning at this point the extreme stability of Innovacoat gold. It will survive 2 hours at 70 degrees C in 2.5 molar sodium hydroxide. So this is a pretty extreme QC test that we use. Materials made with traditional technologies, if you like, will survive. You can't really measure it. It's instantaneous aggregation with this sort of treatment. So we have an extremely stable colloid when we've got the Innovacoat surface. So it's potentially useful for DNA sensing applications, which might be carried out at high temperature, and applications involving small molecules that cannot be irreversibly attached to naked gold. Okay, just coming to the last two slides now. Gold particles can be used for delivery of toxic drugs. So you'll find this type of study in the literature. So cisplatin, which is incredibly toxic, shows reduced toxicity if it's attached to this type of structure. So what we have here is typically an acid-sensitive bond. And when this structure enters, say, a cancer cell, it goes into the endosomes, which are very acidic, then this bond breaks, releasing the cisplatin into the cancer cell, which obviously then kills the cell. So gold nanoparticles used in that way. This is another really interesting use, photothermal therapy, usually done with gold rods, which are blue or brown. So you have, for example, a targeting antibody, which targets the antibody to a tumor, which we show in the patient's arm here. And when the conjugate has accumulated in the tumor, which needs to be near the surface, you then use a laser, and the electron cloud around the gold rod absorbs the energy from the laser, and you can get incredible temperatures. In fact, the rods can actually melt, and obviously in a molten form they turn into spheres, so the heat generated essentially kills the tumor. So I think you can see there are a huge number of applications with gold nanoparticles. These are some of the tools that Innova Biosciences has if you're interested in this area. So we have conjugation kits for 20, 40 and 80 nanometer gold with the surface coat for lateral flow and scattering type applications. The naked gold TEM images that we showed earlier, we've successfully coated all of these materials. So if you make your own gold, for example, and it's, the properties are unique to your way of making the gold, then you can switch to custom coating, covalent conjugation, and get some of the benefits by a custom coating service that we offer. And we can also, as I mentioned, do oriented. We have materials for oriented coupling of whole antibodies, fragments. We have bulk coated gold, especially the 40 nanometer size. We also have materials for attaching oligonucleotides, small molecules, and non-antibody proteins.
So thank you very much for joining us today. We hope that you enjoyed it, and we hope you will be able to join us for the next webinar in September.